Bismillahirrahmanirrahim. Today we are going to study characterization of nanomaterials. Characterization refers to the study of material features such as its composition, structure, various properties like physical, electrical, magnetic, thermal, etc. Characterization of nanomaterials. Nanoparticles' properties vary significantly with size and shape. These particles can be spherical, tubular, or irregularly shaped and can exist in fused, aggregated, and agglomerated forms. The first technique we use is optical imaging probe characterization technique. In this technique, light is used to characterize the material. This contains many methods by which we take image of nanoparticles surface. Confocal laser scanning microscopy, scanning near field optical microscopy, 2-photon fluorescence microscopy, dynamic light scattering, and Brewster angle microscopy are the techniques or methods that we study using light, or we can say which are the part or methods of optical probe characterization technique. Confocal laser scanning microscopy. In confocal laser scanning microscopy, laser light is focused onto a defined spot at a particular point within the sample. Pinhole is used to cut off signals that are out of focus, hence allow only fluorescent signals to enter the light detector. This is the instrumentation of confocal laser scanning microscopy. Light source is laser. Excitation aperture is used to select the excitation wavelength of light from a light source. Pinhole transmits a light to be focused precisely. Then we have a dichroic mirror which allow light of a certain wavelength to pass through while light of other wavelengths are reflected. Objective lens is then used which allow light of the excitation wavelength illuminates the specimen through the objective lens. The fluorescence emitted by specimen is focused to the mirror by same objective lens. Dichroic mirror transmits the emitted light. Emission pinhole transmits the emission range of fluorophore, filter out the entire excitation range of fluorophore. Pinhole cut off the focus signal, or we can say cut out the focus signal. Ocular lens is used to emit light to be focused on the detector. The advantages of confocal laser scanning microscopy involve dynamic behavior studying in live cell imaging. Sensitivity is very high, high degree of specificity, eliminates background noise, and 3D images can be generated. There are certain limitations for confocal laser scanning, which are photobleaching. Fluorophores lose their ability to fluorescence as they are illuminated. Phototoxicity. Fluorescent molecules tend to bring toxic effects on cells. Limited number of excitation wavelengths available with common lasers. Then we have scanning near field optical microscopy. A tiny aperture illuminated by a laser beam from the rear side is scanned across the sample surface and the intensity of light transmitted to the sample is recorded. To achieve high lateral resolution, the aperture had to be nanometer sized and maintained at a scanning distance of less than 10 nanometer from the sample surface. This is the schematic diagram. Moving on to the advantages, we have high resolution up to 25 nanometers, analysis of various properties made possible through contrast using reflection and transmission modes in SNOM, means scanning near optical field microscopy. There are certain limitations as very low working distance and extremely shallow depth of field. long scan times for large sample areas for high resolution images. Then we have two-photon fluorescence microscopy. To explain the two-photon fluorescence microscopy, we must have to know the one-photon fluorescence process, which involves an exciting fluorophore from the electronic ground state to an excited state by a single photon. This process typically requires photons in the UV or blue-green spectral ranges. However, the same excitation process can be generated by the simultaneous absorption of two less energetic photons under sufficiently intense laser. The non-linear process can allow if the sum of the energies of the two photons is greater than the energy gap between the molecule's ground and excited state. Under sufficiently intense excitation, 3-photon and higher photon excitation is also possible, and deep UV visible based on this process can be developed. This is Jablonski diagram for 1-photon and 2-photon excitation, which occur as fluorophores are excited from the ground state to the first electronic state. 1-photon excitation occurs through the absorption of a single photon, while 2-photon excitation occurs through the absorption of two lower energy photons via short-lived intermediate stages. After either excitation process, the fluorophore relaxes to the lower energy level of the first excited electronic state via vibrational process. The subsequent fluorescence emission process for both relaxation modes is the same. The diagram for it is as follows. The major advantages is there is no need of pinholes, no photo-bleaching occurs, no phototoxicity occurs, potentially more sensitive than the previous techniques. The disadvantages is slightly lower resolution because of IR laser used and less expensive. And laser is little bit expensive for this technique. Then we have Brewster angle microscopy. It is a microscope for studying thin films or liquid surface, most typically Langmuir films. It is discovered in 1991. The process or explanation, or we can say the mechanism for this is, in this both the microscope and polarized light source are aimed towards a liquid surface at that liquid's Brewster angle in such a way for the microscope to catch an image of any light reflected from the pure liquid. When both are angled towards it at the Brewster angle, light is only reflected when some other phenomena such as surface films affect the liquid surface. Incident or light, or we can say unpolarized light, is polarized light. We can say that it reflects or it only shows response when we have a doped material. It is used for observe phase changes, shades, packings, monitoring at surface reactions, thin films and doped material characterizations. In the next video, we are going to study the electron microscope, its types, its scanning electron microscopy, and then transmission electron microscopy. For this, goes to the next part mentioned in the videos. Thank you. Allah Hafiz.